Right, we're going to talk about some thermochemistry today. Thermochemistry is going to be examining heat and temperature during physical and chemical changes. So this is a different subset of all the chemistry that we've already talked about, and what we're going to look at is how energy moves during a chemical and physical change. And we can do that because all changes, both physical and chemical, have changes in energy. Energy is transferred from one part of the system to another, but it's always conserved in the system due to the law of conservation of energy. We need to know a couple definitions, and we need to also differentiate between the terms temperature and heat. So temperature is going to be the average kinetic energy of the sample of matter that we happen to be examining. In the case of kinetic energy, it's going to be the energy of motion inside of a sample. Particles are always vibrating in space, and the higher the temperature, the more they are vibrating, or the higher the motion of those particles. For temperatures, in a given sample, there's some particles that have high energy and there's others that have lower energy, but since it's the average, we're looking at putting those together and coming up with the energy of the whole sample and averaging it out. So one way to think about this is that on a cold day, you can have water evaporate. So for example, in the winter, when the snow is frozen, or when there's snow still in your driveway, water is still evaporating. It's at a slower rate than in the summer, but still evaporating, and that's because some of the water molecules have enough energy, high enough kinetic energy, to break away from the rest of the sample and therefore turn into a gas. And then, of course, there's also other particles that have less kinetic energy than that are lower than the average kinetic energy. And that's why temperature is the average of the whole sample instead of just the kinetic energy of individual particles. We can measure temperature in 3 different temperature scales. As far as the SI system goes, Kelvin is the accepted scale. We're going to do most of our work in the Celsius scale for this unit. However, of course, because we live in the United States, the Fahrenheit scale is the one that we use most often. To convert between these, like if you were to measure in Fahrenheit and then you needed to change into Celsius, or if you need to change into Kelvin, we do have equations. One thing to keep in mind are some key temperatures: the boiling point of water, freezing point of water, and then something called absolute zero, which is 0 Kelvin, and that's where all particulate motion stops. Temperature conversions are in these different formulas. So you're going to take the temperature in Celsius, add 273, that's going to be Kelvin. Temperature in Kelvin, subtract 273, that'll equal temperature in Celsius. The Celsius to Fahrenheit, you're going to take 1.8 times the temperature in Celsius, then add 32, that'll be your temperature in Fahrenheit. And then to go from Fahrenheit to Celsius, take your Fahrenheit temperature, subtract 32, and then divide by 1.8, and that'll be your temperature in Celsius. So we talked about temperature, which is the average kinetic energy of the sample. Heat is the sum of all the energy of the sample, which means that heat is an extensive property, and the bigger the sample at a given temperature, the more heat it should contain. So if you take a hot item and you put it with a cold item, heat's going to transfer from the hot item to that of the cold item. It's going to go from the higher kinetic energy to the lower. Heat's always transferred from high to low. And again, the sum total of the entire sample. So one way to think about heat is a cup of water versus an entire lake of water. Both could be at 40 degrees C, 40 degrees Celsius in the hot summer, and the one that is the bigger body of water is going to have much more heat. And one way to think about that is during the winter time, cities that are next to big lakes, like if you're adjacent to Lake Michigan, those cities are always quite a bit warmer than inland lakes. And then vice versa in the summer, especially early summer, cities next to lakes tend to stay cooler because all the heat's going in to warm up the lake, and in the fall and in the winter, all the heat's leaving the lake and warming up the surrounding communities. So those are the vocab words that we're going to need to know: heat, temperature, and then thermochemistry is watching transfers of energy All physical and chemical changes have transfers of energy, and energy is conserved.